over the last few classes you learned recursion and backtracking and AT-hen-to-E2L, powerful ways to break a problem into smaller versions of itself. But we also saw a dark side. Remember naive Fibonacci from the recursion tree class? It calls itself twice at every step, and in doing so, it recomputes the very same values an astronomical number of times. The recursion tree explodes, and a problem that should be trivial becomes impossibly slow. Today we learn the technique that fixes exactly that kind of waste, and in doing so, unlocks a whole category of problems that would otherwise be intractable dynamic programming, usually just called DP. Do not let the fancy name intimidate you and 85-2-fall. The core idea is almost embarrassingly simple. It is this: if you are going to solve the same small problem many times, solve it once, remember the answer, and just look it up every time after. That is it. That is the whole secret. Remembering. By storing the answers to subproblems instead of recomputing them, dynamic programming turns exponential, hopeless recursions into fast, efficient solutions. Today, you will learn the two conditions that make DP apply, the two ways to implement it, and A205, memoization and tabulation, and A205, and how to recognize a DP problem when you meet one. This is one of the most powerful and celebrated techniques in all of computer science. Let us demystify it. Here is our path for today. First, the core idea of dynamic programming. Second, overlapping subproblems. Third, optimal substructure. Fourth, memoization. Fifth, tabulation. And sixth, how to spot a DP problem. Let us dive in. Let us state the core idea plainly, because everything else is just detail on top of it. Dynamic programming solves a big problem by breaking it into smaller subproblems and A212. So far, that is just recursion, which you already know. But here is the one crucial addition that makes it dynamic programming. You remember the answer to each subproblem the first time you compute it. The next time that same subproblem comes up, any A25, and in the right problems, it comes up again and again, any A25, B5, you do not solve it afresh. You simply look up the answer you already stored. Solve each distinct piece exactly once, then reuse. That one move AATE24. Remembering AATE24 is the entire difference between a hopelessly slow recursion and a fast one. Think about naive Fibonacci again. It recomputes Fibonacci of the same number thousands or millions of times. If instead, the very first time you compute Fibonacci of say 10, you write the answer down, then every later time you need it, you just read it off and 812, instantly, no recomputation. The explosive tree of repeated work collapses down to computing each value a single time. So, dynamic programming is, at heart, recursion plus memory. The analogy is doing a big calculation and jotting intermediate results on a notepad so you never redo them. The technique feels almost too simple to have a grand name, and that is a good instinct to hold. The concept is genuinely easy. The skill is in recognizing when it applies and setting it up cleanly, which is what the rest of the class builds. But never lose sight of the one-sentence heart of it. Solve each subproblem once, store the answer, and reuse it. So the takeaway, dynamic programming breaks a big problem into smaller subproblems and remembers each subproblem and tiny 9's answer the first time it is computed. So it is looked up rather than recomputed thereafter, and H2, Volvo-free 8-2-4 recursion plus memory, which collapses an explosive tree of repeated work down to solving each piece exactly once. Dynamic programming does not help every problem and H112, it helps a specific kind. The first of two conditions is overlapping subproblems, and Fibonacci is the perfect illustration. When naive Fibonacci computes Fibonacci of 5, it needs Fibonacci of 4 and Fibonacci of 3. Computing Fibonacci of 4 in turn needs Fibonacci of 3 and Fibonacci of 2. Notice, Fibonacci of 3 is now being computed in two separate places, entirely independently, each redoing all the work beneath it. Go a few levels deeper, and the same subproblems and A212, Fibonacci of 2, of 3 and A212 are being recomputed over and over. an exploding number of times. These repeated identical subproblems are what we call overlapping subproblems. This overlap is precisely the wasted work that dynamic programming eliminates. The subproblems overlap and 84. The same ones recur throughout the computation and 84. So if you compute each one just once and store it, you cut out all that redundant recomputation. The first time you need Fibonacci of 3, you compute it and remember it. Every subsequent time, in every branch, you just fetch the stored value. The explosive, repeated work is gone, replaced by one computation per distinct subproblem. This is the diagnostic that tells you dynamic programming might apply. Does the problem, solved recursively, keep bumping into the same subproblems again and again? If yes, there is overlap to exploit, and memory will pay off enormously. If every subproblem is completely distinct and never recurs an A200 twofold, as in a plain divide and conquer, where you never revisit the same piece and A200 200 twofold, then there is nothing to remember and DP offers no benefit. Overlapping subproblems are the signal that a heap of redundant work is waiting to be saved. Spotting that overlap is the first half of recognizing a DP problem. So the takeaway, overlapping subproblems means the same subproblems recur many times in a recursive solution, and A212 as Fibonacci recomputes the same values over and over an A212. And this repeated identical work is exactly what DP eliminates by computing each distinct subproblem once and storing it. The presence of overlap is the first signal that DP applies. The second condition that makes dynamic programming work is called optimal substructure. It is the property that lets you build a big answer out of smaller ones. Optimal substructure means that the best solution to a problem can be constructed from the best solutions to its subproblems. In other words, if you solve the smaller pieces correctly and A021 optimally and A021, you can combine those piece answers to get the correct answer to the whole. The big problem and D sin D solution is assembled from its parts and D sin D solutions cleanly, without the parts interfering with each other in some tangled way. Fibonacci has this. Fibonacci of n is defined directly as Fibonacci of n-1 plus Fibonacci of n-2 and A212. The answer to the bigger problem is literally built from the answers to the two smaller ones. Many optimization problems share this structure. Consider finding the cheapest path somewhere. The cheapest path to your destination is built from the cheapest path to the place just before it. Because the whole is composed of optimal paths, you can solve the paths and assemble upward with confidence that you are getting the true best answer. Why does this matter for DP? Because dynamic programming works by solving subproblems and combining them an A212. And that only produces the correct answer if the problem actually has this built-from parts property. Optimal substructure is the guarantee that combining subanswers gives the right overall answer. Together with overlapping subproblems, it forms the two-part test for dynamic programming. Overlapping subproblems mean there is repeated work worth saving. And optimal substructure means the answer can be correctly assembled from subproblem answers. When a problem has both, dynamic programming is the tool and 81 to world. You can solve each overlapping piece once and combine them into the whole. So the takeaway, optimal substructure means a problem in N9's best answer can be built from the best answers to its subproblems, as Fibonacci of n is built from the two before it, and 82 1, 12. And this guarantees that combining subanswers yields the correct whole, which together with overlapping subproblems forms the two-part test for when dynamic programming applies. There are two ways to actually implement dynamic programming, and the first is the most natural, memoization, which is top-down. Memoization starts from the recursion you would write anyway. You solve the problem recursively, breaking it into subproblems exactly as normal and A2 on 212, top-down, from the big problem toward the small ones. The only change you make is to add a cache, a place to store the answer to each subproblem once you have computed it. That cache is often just an array or a dictionary keyed by the subproblem. The magic is in one small check at the top of your recursive function. Before doing any work, you ask, and A2020, have I already solved this exact subproblem? A2020, if yes, and A2020, if its answer is in the cache, and A2020, you return the stored answer immediately, doing no further computation. If no, you compute it recursively as usual. But then, before returning, you store the result in the cache so that any future call with the same subproblem gets the instant answer. Check the cache, compute only if it is a miss, always store. This tiny addition transforms performance completely while barely changing your code. You write essentially the natural recursive solution and 8-1-1, the one that follows directly from the problem in 39A's definition and 8-1-1, and by adding a cache and that one check, each distinct subproblem is computed exactly once instead of exponentially many times. Naive Fibonacci with memoization goes from hopelessly slow to instant with just a few extra lines. Namas, this is why memoization is so beloved. It is intuitive. It keeps the clear structure of the recursion, and it delivers the full speed up of dynamic programming almost for free. It is called top-down because you start at the top and 80-12, the full problem, and 80-12 and recurse down, remembering as you go. So the takeaway, memoization is top-down dynamic programming and 8-1-2. You write the natural recursion but add a cache, and at the top of the function check whether the subproblem is already solved, returning the stored answer, if so, and otherwise, computing it and storing it, and 8-1-12, a tiny change that makes each subproblem compute once and turns an exponential recursion instant. The second way to implement dynamic programming is tabulation, which works in the opposite direction, bottom up. Instead of starting from the big problem and recursing down, tabulation starts from the smallest subproblems and works upward. You create a table an A202 of, usually an array an A202 of, and you fill it in order, from the base cases up to the answer you want. You solve the tiniest pieces first, write them in the table, then use those to solve slightly bigger pieces. Write those in, and continue building up until the whole problem is solved. There is no recursion at all. It is a straightforward loop filling a table. Take Fibonacci once more. Bottom up, you start the table with the known base cases. Fibonacci of 0 is 0. Fibonacci of 1 is 1. Then you loop upward. Fibonacci of 2 is the sum of the two entries before it, which are already in the table. Fibonacci of 3 is the sum of the two before it, and so on. Each new entry computed directly from earlier entries already stored. You march up the table until you reach the value you wanted. Each entry is computed exactly once, in order from entries already filled in. The reason tabulation exists as an alternative is that it is often more efficient in practice. Because there is no recursion, there is no function call overhead, and no risk of a deep call stack overflowing and 81 tuple, which can matter for large problems where a deep memoized recursion might hit stack limits. It is a clean, iterative loop. The trade-off is that it can be a little less intuitive to set up because you have to work out the right order to fill the table and handle the base cases explicitly, rather than letting recursion figure out the order for you. But both approaches implement the exact same dynamic programming idea, and 8-212 solve each subproblem once and store it, and 8-212 just from opposite ends. So the takeaway, tabulation is bottom-up dynamic programming, and 8-212 you fill a table starting from the base cases and build upward with a simple loop, each entry computed from earlier ones already stored, with no recursion, and 8-212 which avoids call stack overhead and overflow, at the cost of having to work out the fill order yourself. Since we now have two implementations of the same idea, let us compare them directly so you know which to reach for. Memoization is top-down, recursive, and caches answers on demand, A212. It only ever computes the subproblems it actually needs, storing each as it encounters it. Its great virtue is that it is natural to write. You start from the plain recursive solution, which usually mirrors the problem in 39 definition, and just bolt on a cache. For that reason, it is often the easier one to get correct, especially when you are still getting comfortable with the problem, because you barely deviate from the obvious recursion. Tabulation is bottom-up, iterative, and fills a table completely from the base cases upward. It is frequently faster in practice, thanks to no recursion overhead and no call stack to overflow, which makes it the safer choice for very large inputs. The cost is that you must think about the ordering and A20-012, which subproblems to solve before which and A20-012, and set up the table and base cases by hand, which takes a bit more upfront reasoning than letting recursion drive the order. The reassuring truth is that they are two styles of the same technique, not two different techniques. Both rest on the identical core idea: identify the subproblems, solve each exactly once, and store the answers. Whether you cache a recursion or fill a table, you are doing dynamic programming. A common and practical path is to first think through a problem with memoization, because it flows naturally from the recursion, and then, if you need more speed or worry about stack depth, convert it to a bottom-up tabulation. Know both, and you can always express your dynamic programming solution in whichever form fits the situation best. Same idea, two doors into it. So, the takeaway: memoization and tabulation are two styles of the same technique, and 812. Memoization is top-down recursion with a cache, natural to write and often easier to get right, while tabulation is bottom-up table filling, usually faster with no stack risk but needing you to plan the fill order, and 8-12, and both simply solve each subproblem once and store it. Knowing the technique is half the battle. The other half is recognizing when to use it. So let us build your radar for dynamic programming problems. The first sign is that the problem naturally breaks into smaller subproblems of the same kind. If you find yourself thinking N80-2020, to solve this, I need to solve a smaller version of the same problem, N80-21, you are in recursive territory, N80-2020, the raw material dynamic programming works on. This alone is not enough, but it is the entry point. DP problems are always decomposable into similar subversions of themselves. The second decisive sign is that those subproblems overlap and 80-212. The same subproblems come up again and again as you decompose. This is the crucial one because it is what makes remembering pay off. If you sketch the recursion and notice the same subcases recurring across different branches, that overlap is your green light. Memory will eliminate a mountain of repeated work. No overlap, no benefit from DP. Clear overlap, huge benefit. Learn to look for that recurrence. The third clue is in what the problem asks for. Dynamic programming problems very often ask for an optimal value, and 8-212, a minimum or a maximum, like the shortest path, the least cost, the most value, and 8-212, or for a count, like the number of ways to do something. When you see N82-20, find the minimum, N82-01, N82-01, find the maximum, N82-01, or A2-01, 201. Count the number of ways, AA2-01, combined with a structure that breaks into overlapping subproblems. Your instinct should immediately say N A24S. This might be dynamic programming, or A24N, those three signals together. And A24 decomposes into same kind subproblems. The subproblems overlap, and it asks for an optimum or a count, and A24 are the fingerprint of a DP problem. Spot that fingerprint, and you will know to reach for this technique. So the takeaway: recognize a dynamic programming problem by three signs and A200 dual. It breaks into smaller subproblems of the same kind. Those subproblems overlap so the same ones recur, and it asks for an optimal value, or a count, and A200 dual. And when you see that fingerprint, especially the overlap combined with a min, max, or how many, reach for dynamic programming. Let us turn all of this into a repeatable method you can apply to a new problem. So, dynamic programming becomes a procedure rather than a flash of insight. Step 1. Define the subproblem clearly, in words. What exactly does a smaller instance of this problem look like, And what does its answer represent? For Fibonacci, a subproblem is an 8 हो to पे है. Fibonacci of some number के लिए an 8 हो to 1 है, and its answer is that value. Getting this definition crisp is the most important and often the hardest step any 2 into L. Almost everything else follows from a clear subproblem definition. Step 2. Find the recurrence and 8 Hartwell. The relationship that builds a subproblem in Mind 49. Sons are from smaller ones. This is where optimal substructure becomes concrete. You write down how the answer to a subproblem is composed from the answers to smaller subproblems. For Fibonacci, the recurrence is that Fibonacci of k equals Fibonacci of k minus 1 plus Fibonacci of k minus 2. And step 3, identify the base cases and O202 how the smallest subproblems whose answers you know directly would stop the recursion and seed the table. With those three in hand, an 82 R2 a 5, a subproblem definition, a recurrence, and base cases and 82 R5, the implementation is almost mechanical. Choose memoization. Write the recurrence as a recursive function and add a cache. Or choose tabulation, create a table, fill in the base cases, and loop applying the recurrence to build upward. Either way, the hard thinking was in defining the subproblem and the recurrence. The coding is then routine. This is the real workflow of dynamic programming, and it is far more approachable than the technique in SET9 DSA. Reputation suggests define the subproblem, find the recurrence, set the base cases, then memoize or tabulate. Follow those steps, and a huge range of intimidating problems become tractable. So the takeaway, apply dynamic programming as a method and 80-80 set to house. Define the subproblem clearly in words. Find the recurrence that builds it from smaller subproblems and identify the base cases and 80 set to house. And then the implementation, whether memoization or tabulation, is almost mechanical. The real work is the subproblem and recurrence, not the code. Let us gather the whole class in one breath. The core idea is to break a problem into subproblems and remember each answer so you never recompute it. Overlapping subproblems and A2012. The same sub-answers recurring and A2012 are the wasted work DP eliminates. Optimal substructure means the big answer is built from the best answers of its parts. Memoization is top-down, no more recursion plus a cache. Each subproblem solved once. Tabulation is bottom-up. Fill a table from the smallest pieces upward, no recursion. And you spot a DP problem by overlapping subproblems plus a request for an optimum or a count. Next class NEA21, Classic DP, the knapsack and longest common subsequence problems. One idea at a time. That is dynamic programming.